Alright, so what I wanted to do here, since I'm not going to be around today, is offer you one more example of each type of problem. First, I'm going to do an enthalpy and phase change combined for the transition of something across a boundary and a heating and cooling with that. And then I'm going to do another Hess's Law example. Of course, if you get really stumped with this, you can always talk to Coach Raymaker or wait till I'm back, hopefully tomorrow. But in the meantime, you still have your exam on Wednesday, so I want to make sure you've got some working examples. And so the first thing we need to do in a question like this that involves multiple changes potentially is to identify what's going on. We need the energy needed to convert 50 grams of ice at 273, so that's where I'm at. And I want to take it to water at 323. And so essentially I'm starting at 273 and I want to move to 323. And I know I'm changing phases simply because I want to go from ice to water, so there's a phase change. And so the first thing I want to do then is split this into two independent steps. We're already at the freezing point of water, so I don't have to heat up to get there. So there's no Cm delta T for ice, but there will be a melting of the ice. And then I want to go from this temperature for water to that temperature. So it looks like I've got two steps. So delta H for my process should equal the sum of two heat steps. So I'm going to have a Q1 and a Q2. One of these will be the melting, the other will be the heating up that goes on. So we'll start with finding Q1. Q1 is equal to, it's what it's going to take to melt this. And so anytime we melt something, ice to water, it's going to be N times delta H. And if we're melting something, that particular enthalpy that we're talking about, or heat at constant pressure, is going to be the delta H of fusion. And so that's going to be my first heat step. So let's go ahead and calculate that. So basically I need the moles, and I need to know how much delta H fusion is. Well, we used delta H fusion in a previous problem. I'll just use it here. If I were giving this to you on a test or something, I would give you that value. But you could also look it up in your notes if it's not a test. But what we do need to know that's not given really is the moles of the substance. Now we do know the mass, and so we should be able to find this. So I'm going to say that I've got 50 grams of the substance, and I know the substance, since it's water, is 18 grams per mole. Okay, so that's N. And then delta H, like I said, you can look it up if you want to, is 6.01 kilojoules for every mole of the substance that we see. And so my first step here, the heat required for the first change, is 16.9 kilojoules. And that's adopting the proper significant figures. The next step I have after I melt this stuff, and I've already required 16.9 kilojoules to do so, is to heat it up. So Q2 is a thermal heating, and anytime we do a thermal heating, that means we do specific heat of the material times the mass of the material times how much we heated it by, or the change in temperature for the material. C for water was something you were supposed to know. If not, you need to know it by Wednesday for sure. That's 4.18 joule per gram something temperature. Well, we said we could use degrees Celsius or Kelvin interchangeably. Looks like my temperature is in Kelvin, so I'm going to call it joule per gram Kelvin. The mass we have is still 50 grams. And the delta T we have is to say 373 is where we're going to end up. And we're coming from 323. Fix that. 323. And we're coming from 273. Okay, that's all well and good, but that's going to give me an answer in joules, and I really don't want an answer in joules. I want an answer in kilojoules so I can compare it to this. And so I think we should probably say 1 kilojoule is worth 10 to the third joules, and that will move me into the proper units. And so at this point, all I have to do is find out what Q2 is, and Q2 is equal to 10.5 kilojoules. So now I know how much energy is required for each step, and all I have to do is add them together. And so delta H is the sum of those two energies, both positive, melting and then heating something up. Both of those require energy. So if I add those two together, I get 27.4 kilojoules. Total for this process. So again, both positive, add them together, heating something up, melting something, both require energy. Next problem we have here is a Hess's law problem. And so we're going to be making adjustments to these reactions because these are the individual steps. These three right here are the individual steps that should be able to help me determine my question right here. I want to know what happens when A plus 2C make D, but I don't necessarily want to go do that reaction. And so what I have to do then is look at these reactions and how they need to change, like B goes to 2A, 2B plus 4C goes to 2D plus 2E, E goes to A. Those are steps in this process, but they're not perfect as they are. I've got to make adjustments. And so the easiest way to do this is to locate the very first piece of material that you're going to work with. We're going to work with A here. So I find A down here. Now A is in more than one place, so I don't want to mess with it too much, but I can see that B is not going to be around, and so I need to get B kind of where I can work with it. Now, first thing to note is that A is not a product. A is a reactant, but the first reaction here has it as a product. So I'm going to go ahead and say that this reaction needs to be flipped. And when we flip a reaction, essentially we multiply it by -1. I'm not going to do anything about the fact that there's two A's and I only need one yet because I have another A down here that might help. So I'm going to take this reaction and multiply it by -1. If I do that, I also have to multiply the enthalpy for the reaction by -1. Now, take a look down here at C. We've got 2C. Down here we've got 4C, and C's appear nowhere else. So I've got twice as much. So really I need there to only be 2 C's, which would mean there would be 1 B, 1 D, and 1 E, which means this reaction really is twice as big as it needs to be. And so I'm going to come down to this reaction and multiply it by 1/2. Notice I did not do a negative this time. The C is on the right side of the equation. I just have too much, so I need to reduce that. And then finally, my E to A, well, if I don't think I need to do much with this, I think it's going to work out as it is. Basically, this E is going to help get rid of this E, and this A is going to help get rid of my extra A. And so I don't think I need to do anything but rewrite these and prove that they cancel out. So we have put a negative sign in front of this reaction, which means I don't want B goes to 2A. I want 2A becomes B. And given that, it's not 50 kilojoules, it's -50 kilojoules that's actually going on. Next, we said this reaction was twice too big. We want to half it. So really what we've got going on is B plus 2C becomes D plus E. And when we do that, it's not negative 188 because I only want half of that. It's going to be negative 94 kilojoules. So the reaction's not going to release as much energy as we thought. And then we have E going to A. Well, let's just see what happens if we feed E goes to A in here and leave it at 33 kilojoules. Well, let's see what happens. We want to make sure that we're generating this reaction right here. That's my goal. So I want to make sure that what I have down here adds up as such. So looky here. This A will kill one of those, so I really only have one A. The B's will cancel out, and the E's will cancel out. And what do I really have left? A plus 2C becomes a single D, which is what I wanted. So that means these steps, as written in green down here, are now valid. And my delta H then is just the sum of all these steps. So I have negative 94, and I take away or release 50 more kilojoules of heat. So that takes me up to negative 144. But then this step right here requires 33 kilojoules of heat. So really, I've got negative 144 plus 33 gets me to negative 111 kilojoules for this process as written. And so my question mark right here is negative 111 kilojoules. Just make the changes to the reactions such that you can then begin to create the path you want to create. So just a quick summary, a reminder of enthalpy. Enthalpy has the following properties. It's extensive. That means it depends on the amounts of reactants. Notice in that reaction where we halved it, we halved the energy. It's equal in magnitude but opposite in sign for reverse processes. Notice reaction 1, we didn't change the 50 other than put a negative sign on it. So it's equal magnitude, different sign. And then depends on the states of reactants and products. You haven't seen that yet, but I'll show you an example in just a minute. So to show you it's extensive, just to remind you, looky here, we have 2 hydrogens making 2 waters with an oxygen. If I take half as much stuff, 1 hydrogen with a half oxygen to make 1 water, the energy is divided exactly in half, as you can see right here. Reversible, well, if I'm making water, it's negative. If I break water, it's positive. It takes energy to split water. And then depends on states. If I do the reaction with everything in the gas phase, I do the same, negative 483. However, if I do the reaction where the water becomes a liquid, I release even more energy. Why is that? Well, the liquid water also then had to condense, and to condense to the gas phase, it had to lose energy, and so that's now included in the total for this process, whereas it's not included for the total process in the purple. So some of these things that you haven't really paid attention to in the past are going to be important. One more example, then I'll call it good. I want to give you the following reactions and have you calculate delta H for this reaction right here, 2N2 plus 6H2O. There's a 3O2 plus 4NH3. So we're going to employ the same strategies we used a minute ago. We're going to start with N2, and we're going to find N2 up here. Oh look, I found N2 in reaction number 1. I need 2 of them. That's only a half. So I need to multiply it by 4. Also, I need N2 as a reactant. Up here, N2 as a product. So I need it as a negative. So I'm going to multiply that entire reaction by negative 4. The negative turns the reaction around. The 4 takes me from 1/2 to 2. Next, I'm going to work with my water. I've got 6 H2Os. I'm going to go ahead and write this down such that I flipped it. I've now taken that reaction and written as 2N2 instead of 1/2 N2. My 3/2 of H2 became 6 H2s, and they produced 4 ammonias instead of 1. And the energy there is to just take the energy for the reaction as we had it written, negative to flip it, 4 to adjust the amounts, and away we go. Now, my 6H2O comes from the second reaction. Notice that in the second reaction, H2O is a product. Again, it's not supposed to be. In my reaction, it's supposed to be a reactant, so that's going to mean negative sign. And I need 6, and I only have 2, so that's going to mean negative 3. And so I'll do the same thing I did below. I'll multiply that entire reaction by negative to turn it around, and 3 to get the right amounts. And so now the water is a reactant with a 6. My hydrogen is a product with a 6, and my oxygen is a product with a 3. And so I take negative 3 times the heat. I add them up to make sure it adds up to what I want. Yes, it does. So my 6 hydrogens cancel out, everything else remains.